Hello everyone and welcome. Today we are going to be presenting Western Kentucky University Steel Bridge Team for the 2020 through 2021 school year. The following is a list of team members and faculty advisors who helped to contribute to this project. We would like to give a special thanks to our faculty advisors, Dr. Shane Palmquist and Tyler Baker, for making this possible. We also want to give a special shout out to the 2019 through 2020 bridge team for all the hard work that was put into creating and fabricating the bridge. First, we are going to be discussing the design process for our bridge. One of the main focuses on the design for this project is the simplicity and symmetry of the bridge. Keeping the design simple will in turn cause less confusion during the construction phase as well as add to the aesthetics of the overall bridge. As seen in the bridge envelope, the bridge must meet all dimensional criteria for height, span length, width, and footer positions. With this information, our bridge was designed around all of these specifications. Moving from here, we will discuss the design of the connections and the hybrid style of the bridge. Another focus of the design of the bridge are the connections for each member. Here you can see the design for a male and female nipple for the lateral members to allow for easy connecting of each side of the stringers. The connections are important not only for construction efficiency, but to allow the bridge to stand without any nuts and bolts holding the members together. The bridge is a hybrid truss beam style design with a simple truss as the stringers and beams for the compression, tension, and bottom lateral bracing members. The benefits of a hybrid design is the additional support provided by the tension and compression members during the vertical loading. With the use of design software, we were able to create a bridge that will meet all of the criteria and perform under each load case. The following is a short clip of the completed 3D model of the steel bridge.
Next up, we will be discussing the analysis and calculations for the project. The hand calculations were calculated with the deflection equation for a simply supported beam. Using these three load cases, we were able to see how the bridge would deflect. We used these gauges, as seen in the picture, to measure the deflection during three different load cases. This table represents the measurements obtained through loading of the bridge. Multiple gauges were used for measuring and averages were taken to obtain an approximate deflection. The following shows the free body diagram representing load case number 2, which applies 1,000 pounds 5 foot 6 inches from the end of the bridge and 1,500 pounds 11 foot 6 inches from the same end of the bridge. The shear moment diagram for the same load case shows the maximum moment that occurs during vertical loading at the location of the 1,500 pound load. A computer modeling software called Visual Analysis was used to model the bridge and load it along the stringers based on load case number 2. The results showed a vertical deflection of 0.154 inches and lateral deflection of 0.026 inches.
Lastly, we will talk about the construction method of the bridge. After the completion of our design with our modeling software, we were able to determine the total number of members for the entire bridge construction. Each member was designed to be in compliance with the bridge specifications. From there, each member that was created was joined together with an appropriate male and female ends and secured with a nut and bolt. The decision of material to construct the bridge was determined based on the total cost of the material, the strength, and the workability of the material. With these requirements, alloy 4130, known as chromoly, was a perfect fit. Following the same thought process to create a simplistic bridge design, the construction of the bridge was intended to be as simple as possible. The entire bridge is designed to be assembled with only a drill and a rubber mallet. The connections of the bottom lateral members were designed with a male and female nipple that allows the members to be slid into place and rotated to lock the members together, saving on construction time. Another efficiency and innovation was to weld the nuts to the end of each member. The nuts are positioned in a way to allow the builders to easily tighten bolts once members are connected. For structural integrity and aesthetics of the bridge, each male and female connector that was welded into the ends of connecting members was done so with a technique known as a plug weld. The weld is just as strong as the circumference weld and adds to the aesthetics of the bridge. The table shows a comprehensive list of the required materials for construction of the bridge. This includes the quantity of steel for members, nuts, bolts, and connections. The total cost is listed for the entirety of the materials.
The sequence for the construction will be as follows: connection of legs, stringers, lateral, compression, and tension members, and finally bolts. From here, we will discuss the details of each portion of the construction sequence. To start off construction as shown here, one leg will be placed in the footer on both sides of the river on opposite sides of the bridge. From there, the stringer members will be constructed by either side meeting in the middle of the river while simultaneously adding bolts to hold the members in place. The stringer will be finished from the opposite side that it was started from and connected to the other legs and placed in the footer. Once the stringer was constructed, the bottom lateral members will be slid into place and rotated to lock the members as shown by the 4 locations here. The compression members will be constructed along the top of the bridge, connecting from one end of the bridge to the other end as shown here. The tension members will be constructed connecting the compression member to the stringer of the bridge in the 4 locations here. All bolts holding each member together will be tightened, resulting in the completion of the construction sequence.
Due to the innovations of connections, the bridge construction speed will be improved, resulting in more cost-effective bridge design. As stated previously, the advantages of a hybrid design with components of a truss and beam bridge will increase the capabilities of bridge loading. This marks the end of the presentation for our steel bridge project. Thank you for listening.